All right, welcome back. Here we are in Module 4 now. So I'm going to break this module up into two separate lecture videos. So the first one's going to be the first 3 sections, and the second one will be the last 3 sections. So we're going to go up through two-dimensional arrays. They call them grids. They're also a matrix. We'll deal with these first 3 concepts, and then we'll break, and then we'll come to the next video on the backside. Okay, so let's talk about this array data structure. An array can be multidimensional, depending on if we're talking about data science or if we're talking about traditional programming. We look at arrays as being either one-dimensional, two-dimensional, three-dimensional, or n-dimensional in reality. For this aspect of the lecture, we're going to talk about one-dimensional arrays. Now, the array class, it's a built-in class. We've talked about it before. It comes from the NumPy, N-U-M-P-Y library that we have to import. When we get that array class, it comes with some built-in functions. There's an init function, or it initializes, or I like to compare that to the constructor. There's a len function that tells us how long this thing is, and when we've got these double underscores, those are built-in functions. And when we call them, we may call them explicitly or we may call them implicitly. I'll talk about that here in a second. So we've got init. It initializes or constructs the object. There's a length. Convert it to a string. There's an iter function that allows us to iterate through the array. That's what this for loop is. Having the iter function is implicitly invoked when we do this for item in A being the array. That allows us to walk through each iteration of the array. This random access at any point, we're allowed to do that, or walk through it using iter. A index get item, that's our random access. The iter walks through, get item, goes to a specific index in the array. Now, we're implicitly using the get item function when we say a index. That goes and gets whatever the value is there. If I assign a value to a position or an index in an array, that's the set item. All right. We'll call those accessors and mutators. Gets, access the value. Sets, mutate or change what's there. So these are built-in functions that we can use that are in that class. We use them implicitly for the most part. Len, that's explicit. String, that's explicit. Typecasting. If I say A equals array 10, that's implicitly invoking the constructor. And essentially what we're saying is, and we look at this as the constructor traditionally, name of the class, and some arguments we're passing to it. Well, we're actually doing more than that, but when we look at the init, it's got capacity. We're passing it that, 10. Fill value, we're not giving it anything to put in there, we're just giving it the length of how long this thing's going to be. We didn't put anything in it. So we reserved, I talked about it before, a block of 10 storage units in a row. I got 10 storage units in a row when I constructed this instance of an array class called little a. I say, well, how long is little a? Well, this gets a bit of a gray area, and we're going to talk about that in a little bit. And that's when we deal with the concept of logical and physical memory. I reserved 10 places in physical memory when I did this. How many of them actually have something in them? None. I didn't pass anything to it, so there's nothing in there. Since there's nothing in there, if I said, hey, let's go use this array to go do something, sum up the values in it. I don't have any values in it. Logically, there's nothing there to add up. How much space do I have? You've got 10 spaces, but there's nothing in them. Nothing I can do anything with. They're empty. So here's an example of this array class. We create the object A using the init function. A is the name of the object we've created, so that's, we call it self in the class itself. Even though I know, since I'm talking about A, that's A, this go. If I created one B, that's self. So self refers to the name that I gave to whatever this object is. It's an implicit kind of thing. Capacity, how big do you want it? What are you putting in it? By default, you don't have to put anything in it. Or if you got something, give it to me, I'll put it in there. Self.items equals list. So we're using a list function to create or populate this array. For count in range capacity, we append anything to the end of the list. Wait a minute, I thought this was an array. It is an array. In this example, this is, I want to say, a fictitious array. It's not really a true array because this isn't NumPy. This is the author saying, hey, let's go create our version of an array. And we're going to implicitly create our own version of an array. It's not a real array because, what is it? It's a list. But here's a way to, without using NumPy, logically have our array class. Prefer to use NumPy, and we will in different examples. So with that said, we've created this array class. I can call it or invoke it at any point and do what I want to with it. It helps us logically understand what's taking place when we look at it from this example, but just keep in mind what we just saw. It's a list, and the rules of a list are different than the rules of an array. Now, if it's a list, these rules don't apply. What we're looking at right now. This is if this were actually a NumPy array, this is what we would have. The machine address, the physical address in memory, sequential. Like the example I used was one storage unit right next to the other, next to the other, next to the other. Index 0, 1, 2, 3, 4. The data is saved in contiguous memory, meaning they are right next to each other, one right after the other. Now, when we do this, we can access randomly anything in that contiguous memory. Pretty doggone fast because it's next to each other. I don't have to go reach out and find things over here, over there, over there. And if I'm looking at a list, it's different than this. A list appears to be like this, but the addresses are different. They're not sequential. The indexes are sorted like this, but where these things are stored is not right up next to each other. It's different. I can still access these things randomly by their index. It's just where I have to go to physically get that value or change that value is not the same in a list as it would be in an array. Okay. So with that said, we've got static memory and dynamic memory. Static memory is an example of a tuple. Dynamic memory is an example of an array. Okay. In a tuple, I can't go in and randomly access anything in it and change it. It's static. It exists the way it is. If I want to modify something in that tuple, I have to rewrite the whole doggone tuple, or essentially replace it. Dynamic memory, if we look at what we saw back here, I can go in and access any of these places in memory by using the index, access that little block or that little storage unit, get what's in there, or change, modify what's in there. That's huge. I have the ability to change individual little items in there. That's the dynamic memory. I have the ability to change things that are in there because of the data type that I'm using. Now, this physical size and logical size. The physical size is how much space did I rent or reserve. If I'm talking about I'm renting storage units, if I rented a block of 10 of them, that's my physical size. The example that we saw, we didn't put anything in that little A array that we created. Physical size was set. Logical size is how much stuff is in there that are currently available to the application that can actually do something with. So there's a distinction between logical size and physical size. Physical size is how much space I reserved. Logical size is things I'm actually doing something with. Now, in the examples that we talked about before, we kept using, when we were talking about algorithms and time complexity and big O notation, n. And what if n is really, really, really big? Well, the examples that we saw, n was 10. Well, how much memory did I have? How many spaces did I have reserved for that array? Was it just 10? Or was it potentially bigger? Let's say I had 20 spaces of physical memory available to me. I only had 10 things in it. I want to insert into that array, no worries, I've got space to grow. N just increased by 1. N is my logical size, not my physical size. Physical size is the space that I have available to do something with. At some point I run out of physical size or physical space. I need to create more space, reallocate space, or allocate more space. And when I do that, I essentially do the equivalent of, let's jump back here, this right here. Look at this function. Let's assume I have an array and I reserved 10 places in memory. Capacity, the first time I created it, was 10. And so you know what? I need to add another value to it. If that's the case, and we're talking small numbers, we traditionally will say capacity will equal n times 2. I'll take whatever the capacity I had before and I need to double it. If I need more space, I'm just going to double the amount of space that I had. If I filled up, then n is how much space I had available. N, or I should say logical and physical, are one and the same. Now I've run out of space, I need more. So I want to increase physical space because I don't have enough room for one more n plus 1. I don't have room for n plus 1. So I literally invoke this function again, pass it n times 2. My physical space got bigger. Fill value is everything that's in my current array. You know what? Self is, that's the same name. I'm going to name this new one the same as the old one. I populate the new one with everything from the old one. Delete the old one. I've got a new array, just like the old array, but physical space just got bigger. I've got more room to grow if I need. And by it being contiguous memory, it's more efficient than if it's non-contiguous memory, like a list where I've got to go all over potentially trying to find data. And I'm going all over where? I'm going all over in RAM. I said, well, RAM's not that big, is it? It's not big when we think of it in terms of space, like when we're looking around our house. It's not big like that, but we look at it in terms of the capacity. If I have a terabyte of RAM, that's a lot of little spots that I can store stuff. And if they're not contiguous, man, that's a lot of little things that I got to go through to try and find what I'm looking for. So that's the difference between physical size and logical size. Here's a good example of it. The default capacity is 5. Logical size is 0 because I haven't put anything in it yet. A equals default capacity. So I defined an object. It's an instance of the array class called little a that has a physical size, default capacity, of 5. What's in there? Nothing. Can't really do anything with it. All right. If I want to increase the size of an array, that's something I just talked about. If it's little, not really, really big, double it. You'll create or reserve double the space, take what you've got, put it in the new one, give the new one the same name, get rid of the old one. It's simple as that. If I want to decrease the size of the array, I'm doing the same thing. I'm just passing it a little number. I'm passing it a little number. I don't know how much smaller I need it to be, but can I get away with 1/2 the size? Is that okay? 1/4 the size? I don't know how small I need to make it, but essentially all I'm going to do is call that constructor, that init function, pass it the new capacity, pass it my existing items. My physical size just was reduced. That's what decreasing the size of an array is. My logical size didn't change. My physical size did. I can make my logical size smaller and not impact my physical size. All that means is I'm deleting an item in the array. Now, if I'm deleting an item in an array, let me look at inserting an item into an array. And this array that I'm inserting an item into, I'm dealing with logical space, not physical space. The logical length of the array will grow by 1 when I insert an item in. And I need to find out, where's this thing going to go? Where is this item going to go? And I want to sort this thing out. It's already in ascending order, and I want to add a new item to it. I've got room at the end. So what I'm going to do is I take this new item and I put it at the end. And I look at the new item and the one before it. I say, is the new item smaller than the one before it? If it is, let's swap them. That's what's happening here. I put the new item in, and if it's different, I swap it. And now it's in position 3. Swap it if needed. Swap it if needed. No. And essentially, I'm going through and I'm swapping these things as needed, shifting them into the position they need to be. I'm looking at it as I'm swapping it up, but they're looking at it here as, well, we're swapping it down. So I put my thing here, I compared it to the last one, and if it's the last one, I move this one down, insert mine into index 3. Compare it to 2, or index 2. Let's swap that. Swap that, swap that. And essentially I end up with what would have been in the end here in index 1. I just walk it right on up there. Everything else walked right on down. So that's inserting. What about I want to delete an item in a list? Well, we go about it the opposite way. I say, you know what? I want to get rid of what's in index 1. So I want to get rid of what's in index 1. So, okay. Take what's in index 1 plus 1, 1 being I. Take what's in index I and overwrite it with what's in index I plus 1, and then increase I by 1. Okay. Take what's in index I plus 1, which is 3, and overwrite it. Overwrite it. And when we're all done, I just delete whatever's in the end in that last position, and that's what I've got left. My logical space shrank by 1. My physical space didn't switch at all. Now, we're talking about running times and different operations. And in this table, they talk about the I position. And I being, I don't know, it's whatever the index is. So I want to access any position in an array. So the ith position is literally any position. The best case scenario for accessing any position in an array is constant. I know what the position is. I just go to it. Because I can randomly access any index in that array. Doesn't matter if it's sorted or not. I'm going specifically to one index. Constant time. Big O 1. That's constant time. What's the worst case scenario? Same. It's not going to take me any more than one task to get to any of those positions. If I want to replace anything in there, one action. Best and worst case scenario, constant. Insert at the logical end. Whoa, wait a minute. The logical end. That's n plus 1. I know where that index is. Constant time. Insert at the nth position. Why is this big O to the n and not constant? Well, because I'm inserting to the nth or the ith position somewhere. I want to insert somewhere in this array. For me to insert into the array means that some things got to move. Some things got to get pushed back. And if things got to get pushed back, man, I could have to push everything back. If I put it in the front, everything's got to move back. If I put it in the end, nothing's got to move back. So it could be 1, or it could be n. Remember what I said about theta? Theta is our average. So always plan worst case. It's n. Whatever the length is how far I'm going to go with my average case. So I wouldn't show it in a symbol of big O of n average case. I would say, what is the theta of n for that task? Insert and remove both the theta of n. The theta would be n. Average case would be n in big O notation. I want to increase capacity. Now, this one, it may seem a little confusing, but if you think back, increase and decrease. What is it that I have to do that takes time? I call the constructor. I call that init function. That doesn't take any time. The thing that takes time is going through the array and writing from index 1 to index 1, index 1 to index 1, old one to the new one. Naming it, that doesn't take time. Amount of space, not a big deal. That's constant. It takes me 1. You do it once. The thing that takes time is how long is the logical memory? So that's the n. So best and worst case scenario is n. It's going to take me n times every time. N is our logical length of the existing array. What I have to have to write from one to the other. Remove from a logical end. That's pretty easy. I go to n over n minus 1 and delete it. One action. There weren't multiple iterations. Insert at the ith position. Well, it's the same that we did before. I don't know why they're showing it twice. I don't know why they're doing this again. It's redundant. Okay. Now, let's talk about, they call them two-dimensional arrays or grids. It looks like a spreadsheet in Excel. It's a matrix. In math, we'll call it a matrix. It's a two-dimensional array. Some may call it a grid. It has height and width. If you have a one-dimensional array, how many for loops did it take for us to find an item in that one-dimensional array? Let's go search for the number 10. 4 items in that array. I don't know how long it is, n. 4 items in A. If item is equivalent to input, whatever the value you're looking for, return I, whatever our index is. I want to go through and find out the index of whatever I'm looking for. If it's not there, return -1. Now on this, I need one for loop to go through this one dimension. But this is not a one-dimensional array. It doesn't just have width or length. It has height. I need another for loop to navigate through this axis. Here's an axis. I need a for loop to walk through each item in the one dimension. This is a dimension. As I walk through each item in this dimension, if it was one dimensional, they're not columns, they're just the index. But since I'm looking at it in 2 dimensions, here's columns. I need a for loop to go through each column, and I need another for loop to go through each row. Whichever one you want to go through, if you want to go through row by row, then row navigation is the outer loop. Column navigation is the inner loop. If you want to go column by column, column is the outer, row is the inner. It could be a 3-dimensional array, conceptually same thing. That'd be 3 different nested loops, depending on the order that you're going through them. Okay, you would go down one layer at a time, or one specific column or row in that layer. Now, with that said, we're going through and essentially doing the same stuff that we did in that array class that we saw before. But instead of just having one dimension, physical length, or physical size they called it, we have two. How tall? How wide? Okay. So it's going to work pretty much the same thing. They're calling it a grid here. It's a two-dimensional array in NumPy. Deal with it a little bit different than how they're talking about it here. But we're going to go through it. It's like I said, we're going to go through nested for loops. One goes through the height, one goes through the width. Columns is the width, rows is the height. Okay. They create this grid class. Now, hold up. This is essentially the same thing we saw before. Self, instead of physical size, or how big do you want it, number of rows, number of columns. Okay. This is structurally about the same thing that we dealt with before. Structurally about the same thing we did before. But what we're doing here is this gets a little confusing because we're going row by row and we're calling that other class that we had. So we're using the array class and the grid class. The grid class has two values, the array class has one. So conceptually, it's about the same thing. We're just adding another parameter to what it is we're doing. Structurally, about the same thing. Now, time complexity for a two-dimensional array. Ooh, things get ugly. Things that would have been n are now n squared. Things that would have been n squared are now n cubed. It gets crazy. But it's not, it doesn't have to be so bad. So we call it a matrix now. They're changing the names back and forth. It's a matrix. Get used to the word matrix for a two-dimensional array. We've got, instead of len, we've got get height or get width. So we've got some more functionality built in it. We went and dug in here. Get width, get height. I don't see len. Get an item, convert it to a string. I need to have set an item as well. So there's more than just what we see there. Okay. So this is as far as I said I was going to go in this example. Keep in mind these structures that they gave examples of. The author, how they've set this book up, uses basic Python only. And we're creating imaginary arrays. They are not true arrays with contiguous memory. A true array is contiguous memory. These examples that we've created, they're really one-dimensional and two-dimensional lists. If we want to do things the way it's really done, we'll use NumPy. NumPy has slightly different functionality built into it, but conceptually, what's taking place is very similar to what we saw in that grid class or in that array class. Okay. We'll dig into arrays a little bit more. You can use those notebooks that I provided back in Module 1 to access a refresh on the array data type And that does utilize the NumPy array and navigating, manipulating the NumPy array. Okay, I'll see you in the second half of Module 4.